Okay, so let's move on to our new section. So in the previous section 4.2, you learn reduction of order method, right? So if you have a second order linear homogeneous differential equation, according to the version of the reduction of order method that you learn, if you know a one solution, you can find that second piece, right? Y2. Okay. How about if we want a method that we can find both y1 and y2, that we don't need to know y1 to find y2? That will be so great, right? Now that is what we are going to learn. The method that we are going to learn today is going to get repeated, going to get used in several future sections. So this is a super important section and often students find this lesson very enjoyable. Okay, all right. So to use the method that you're going to learn today, you need to have a linear, homogeneous differential equation. It doesn't need to be second order, but let's start with second order differential equation. Later we can learn higher order ones too. Okay. All right. There should be another one condition too. Linear, homogeneous, and the other condition is coefficients of your differential equation have to be constants. See, A2, A1, A0 are constants. That's the one other conditions. You can't have like x squared times y double prime, x times y prime. No, your A2, A1, A0, your coefficients have to be numbers. Okay, all right. However, so if you get such a differential equation, now this is very interesting. Think about a solution, a proposal solution. These solutions should have a special property, because if you look at this differential equation, what you do is you take your solution and you take its own derivative, first derivative, then you take your own second derivative here, and then you add them together, right? That is what is happening on the left hand side. So you add your own derivatives to yourself. What happens is that you get 0. Right? You multiply your derivatives by constant, you add them and you get 0. So this y have to be very special, right? Because you cannot do it for every function. Okay? Think about sine. Sine and cosine. So derivative of sine is cosine. Can you add sine and cosine and get 0 by multiplying by some numbers other than 0? No, right? You cannot. So what is the special format of y? Okay, I say we assume the special format of y is look like e to the mx, where m is a real number or a complex number. So we assume your solution look like e to the mx. Okay, m is a number and that is what we are looking for. We have to find that m. Okay, all right. Now wait a minute here. Now this is a second order differential equation. Now I need two solutions, right? I need those two linearly independent solutions, because then we can form the fundamental set of solutions. Now you only give me one solution. Where's the other one? That's a problem, right? Okay, let me show you how we find that. Let me show you the methodology. First thing we do is we assume our solution to be in this format. Let's find its derivative. So the derivative of e to the mx is me to the mx. Second derivative is you take another m out, m square e to the mx. Okay. Now what I'm going to do is I am going to substitute all these three into that differential equation. So a2 times m square e to the mx plus a1 y prime is me to the mx, a0 is a0, y is e to the mx. Okay. Now let's try to simplify. The left hand side, we can factor out e to the mx, right? You will be always doing that, okay? So we can factorize e to the mx. Good. Now on the left hand side, we have a second degree polynomial and an exponential function. When you multiply them, you get 0, right? That is what this equation says. Hang on a second. Can e to the mx be ever 0? No. Exponential function is never 0. So who should be 0? Yeah, the quadratic function there. second degree polynomial, that is what should be 0, right? Otherwise you cannot get 0 on the right hand side. So this should be definitely 0. Now this is a quadratic equation. Now do you see why we did some practice on quadratic equations in the preparation quiz? Yeah, you're gonna get a lot of quadratic equations in this lesson, okay? All right, good. Now, you didn't still tell me how we can find two solutions, because we still say y is equal e to the mx is the solution. But where are two solutions? Don't we get two solutions from this equation? Think about it for a minute. Yes, right? We can solve this quadratic equation for m. Now tell me, how many roots should you get? Two roots, right? So you should get root m1 and m2. Okay, now do you see the two solutions? Yes, right? So there are several scenarios that can play out, but this is the big idea. Okay, you think your solution to be e to the mx. You substitute that into your differential equation. Then you get the second degree polynomial or the quadratic equation. We call this the auxiliary equation of the differential equation, the polynomial. So if you have a second degree differential equation, you get a quadratic equation. If you have a third degree differential equation, you will have a third degree polynomial. Okay, so we call it the auxiliary equation, or some people call it characteristic equation. Okay, when you get the auxiliary equation, you will factorize it, or you will use the quadratic formula, and you will get these two roots. You can get two distinct roots, then you can find the two fundamental set of solutions. Sometimes you might get the same root, two repeated roots. We saw that in the preparation of quiz, right? We will learn in the future what can we do if you get that situation. Sometimes we can get complex roots. How can we find the two solutions if we get complex roots? So in future videos, what we are going to do is we get this auxiliary equation and we are going to learn how can we construct these two solutions, or the fundamental set of solutions y1 and y2 given these two roots. Okay, all right then. Thank you very much.